In this video, we'll try to derive values of trigonometric ratios 0 and 90. So let's just first start from the beginning, and then we'll end up getting values for 0 and 90, especially at least sine, cos and tan. So other ratios, depending on those ratios, so you should be able to substitute these values and find the other values of secant theta or cosecant theta. So let's try. First, let's draw a ray. Let's call this A, and let this be B, and another ray which is actually making certain angle. So all these things we have learned even from previous standards as basic things. So let's call this C. I'm going to draw a perpendicular here. So main thing is we are trying to come up with a right angle triangle. One of the reason is that I can actually use Pythagoras theorem with this to find the sides. Pythagoras theorem. So in this scenario, I've taken AB as a ray and then AC as another ray which is making an angle of theta. Let me call that angle as theta. So in trigonometric, usually what happens is when we find out angles or sides based on other angles or other sides which are given. So we find out if there are two angles given, third angle or otherwise based on the other ratios. So but we find out by using trigonometric ratios. We call them as trigonometric ratios. So these trigonometric ratios are sine theta, cos theta, tan theta, cot theta, secant theta, cosecant theta. These are the ratios. So here theta for all of them is an angle represented in that triangle. Usually it is an acute angle. If not, if you are considering 90, we'll try to see how we find out the value of 90 here. So before that, what we'll do is we'll try to understand how to write ratios depending on sides of a triangle for these trigonometric ratios. Sine theta, before that let's understand something else. If this is theta, this is the angle I am going to take. Anything opposite to that is actually going to be opposite side. Theta, that will be opposite side. This will be my adjacent side. Because it's a right angle triangle, so this is actually going to be hypotenuse. Sometimes in some textbooks or in some schools, you will also learn this as terminology will be something like this will be perpendicular, this will be base, this will be hypotenuse. So in this scenario, I'm actually going to use opposite and adjacent and hypotenuse. To get sine theta, I need to have the ratio of opposite by hypotenuse. In this scenario, what do you have? Opposite actually represents CB and hypotenuse is AC. Similarly, sine theta will be equals to adjacent divided by hypotenuse. So adjacent in this scenario is AB divided by AC. Tan theta, once you know these two, you can actually write any of this. I have another video on the ratios and also how to find the values of other angles which are 30, 60 and 45. These ones, not the derivations, at least how without memorizing how you can write those values. Watch that video if you are interested. So here we are trying to concentrate on deriving the value of trigonometric ratios for 0 and 90. So tan theta can be written as sine theta by cos theta. Sine theta by cos theta. These two, I can just straight away take the value of this and write it here. If this divided by this, what is going to happen? AC gets cancelled. So which is my opposite by adjacent, which is AB, which is opposite by adjacent. Either you can remember this or otherwise remember that particular ratio, how we wrote tan theta equals to. So based on these two, you can write all of them. You don't need to memorize any of this. Now we'll keep this aside and we will try to find out the value for 0. Let's see. If I'm actually going to take, this is for 0 degrees, right? If I'm going to take the same diagram, this is theta and that is B, and there is a perpendicular drawn from that another ray for that angle. So to find 0, that means theta equals to 0. How can I get theta equals to 0? Let's start. If I'm going to assume theta is some 40 or 45, I have to reduce this to 0. I'm going to draw a series of diagram here so that you can understand. Let's try. So this will be AB. Just stay with me. You will get to know exactly what I'm trying to do. So I'm going to reduce that angle. Theta, I have reduced it. That perpendicular still stays and C still stays there itself. So I'll reduce it further. Sorry. I'll reduce it even further. That is C, that is B, and here is theta, there is theta, and this is A. So what is going to happen when I reduce it even further? The last thing, even before it is going past AB. So it's actually AC is actually going to lie on AB. So that means that when I bring that down, theta, bring that down to 0, A will be here and C and B, both of them will coincide each other. So what does that mean? Theta angle is 0 and AC becomes AB. AC equals to AB. Okay, now we said that. Now what's going to happen to CB? CB, when I started reducing theta angle, CB, the height or the length of that side started reducing as well. When theta became 0, AC was lying on AB and length of AC became equals to AB, and CB is nowhere to be seen. So that means the length of CB is actually going to be 0. Length of CB is 0. Now let's try to find out what's going to happen to our ratios. So sin theta, according to this, it is CB by AC. So what does that mean? My sin theta is CB is 0 divided by my AC. It doesn't matter now what value I have for AC or AB. So value of sin theta, or sin in this scenario, sin 0 is actually going to be 0. So sin 0 for the value of theta 0 degrees, it's going to be 0. Similarly, cos theta will be equals to AB by AC. That's based on this. But remember, when we started reducing that theta angle to 0, it was lying on AC, started lying on AB because theta was 0 and AC became equals to AB. So that's what we wrote here. If AC equals to AB, what's going to happen? Cos theta in this scenario 0 AC divided by AC, or otherwise you can substitute AC as AB, one of them. They both get cancelled, that will be 1. So cos 0 is actually going to be 1. So you got two values here. So sin 0 is 0 and cos 0 is 1. Let's understand what happens to 90 degrees. It's just the opposite. Let me draw a series of diagrams here so you can understand what is going to happen. I'm going to take the same diagram. That is B, that is C, that's A, and that's perpendicular. That's my theta angle. Now theta actually has to become 90. So what is going to happen? Let's draw some diagrams here. So theta, I will increase this little bit further. That is C. That will be B. This is actually going to stay 90. This is not going to change, perpendicular. I'm actually increasing theta value so that I can reach at one point theta equals to 90. So let's draw one more diagram. B, that is, sorry, here actually this is supposed to be, this is C, that is C, that is A, right, that is theta. So when suddenly theta becomes 90, that is my theta, theta becomes 90, what is this line? Line is actually going closer to AC. BC is going closer to AC. So that means at when theta becomes 90, BC will lie on AC. So this keeps on going closer, and then when this becomes straight here, this will lie on that. So that means here C will be there and B will touch A and B will be there. So BC will lie on AC. So what happened here? According to this, now we brought it down, AC equals to BC. So we took the diagram, started increasing theta. As we started increasing theta, we kept this 90, the previous one, as is. So that BC line started moving towards left, and then at certain point of time when theta became 90, BC is going to lie on AC. So that means BC will be equals to AC. But something has changed here. What happened to AB? AB, as you can see, AB started reducing. And when theta became 90 and AC became equals to BC, AB became 0. It has become 0. So AB started reducing. A and B are lying on same thing, and then AC is equals to BC, AB becomes 0. Now if I write the same thing, sin theta will be equals to CB by AC according to this ratio what we have written, CB by AC. So here what is CB? CB and AC, or BC and AC, are same. So I can substitute one of them. That will be 1. And cos theta is equals to what happens? AB by AC. AB by AC. AB by AC. So now AB is 0 from this. 0 by AC. Doesn't matter whatever value we are going to take for AC, that's actually going to be 0. So this is 90, and that is 90. So sin 90 is actually going to be 1, and cos 90 is actually going to be 0. Understand how this line starts moving towards AC, and that perpendicular stays as is, nothing changes in that. That keeps moving. At one point of time they both lie on the same line, and AB vanishes here, and in this case CB vanishes here. So depending on that we have put the values, and we have taken the sides as equal when they started lying on each other. If we substitute those values in our ratios what we have written for these trigonometric ratios, we got sin 0 and cos 0 and sin 90 and cos 90. Let's look at deriving angles 30 and 60. So while deriving angles ratios for angles 0 and 90, what we did is we tried to reduce the angle, and then one of the side was equals to the other one, and then one of the sides actually vanished. So that was easy because where we were able to represent one of the side length of sides into another side, and then one of the side we took it as 0. But whereas 30 and 60, which are two acute angles, as you can see these two are acute angles. If I am actually going to consider a right angle triangle, this can be 90, and then another one can be 30 and 60. That actually makes angle some property as 180 for a triangle. But the problem with this is I can mention the angles, but what about sides? There actually we were able to mention the length of one side into the other one, and then another one, the third one actually turned into 0. But whereas here I can't just take a b c, or this is a and this is 2a, or this is b. So I can't just put some values to the sides. So for that reason, what we are going to do is we'll just try to consider equilateral triangle. That equilateral triangle, if I take equilateral triangle with 90, then what is going to happen? If that is 90, how can this be an equilateral triangle? Because in an equilateral triangle all angles are supposed to be 60. So one cannot be 90 and then I still expect the triangle to be equilateral triangle. So that is not a possibility. So we'll just take a normal usual equilateral triangle. The reason for this is I know the sides of the triangle A, A, A. You can take anything X, 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 A, or anywhere. But I know the lengths, all the lengths of this triangle are equal. So keeping that in mind, let's name the vertices ABC. We are concerned with 30 and 60. So we need 30 and 60. The only way we can come up with 30 and 60 is, so let's draw a perpendicular which is actually going to be angle bisector. Median, which is AD, also perpendicular because it's an equilateral triangle, that also bisects the angle A. So if this is an equilateral triangle, if all of them are 60, 60, 60, what is going to happen? That will be 60, that is 60, and this angle bisector 60 divides into 2. So now I can see that there are two triangles ADC and ABD. I can take one of them. But now let's look into that. If I am actually going to consider one of these triangles, what happens to the side BD or CD, which is actually going to be A by 2? This is supposed to be A by 2 and this is supposed to be A by 2. Just so that I want to avoid this fraction, what I'm going to do is I will take each part as A itself. Each part as A. So then what happens? If I take this as A and if I take this as A, the length of BC is actually going to be 2A. So that means I have to make this 2 equals to 2A, because we have considered this triangle as an equilateral triangle. 2A, 2A. Now everything makes sense. I'm just not going to work with the fraction. So let's consider triangle ABD. Right angle at D. In that angle, what do I need? Even if I want to write the ratios of trigonometry, for all this I know AB is 2A, BD is A. I don't know the length of AD. So let's find out AD. So what's going to happen? If I apply Pythagoras theorem for that right angle triangle, hypotenuse square, which is AB square, equals to AD square plus BD square. So AD square will be equals to AB square, and if I transpose it that side, it will be minus BD square. AB, we know AB as 2A whole square minus BD as A whole square. This is going to give us 4A square minus A square, which is equals to 3A square. If I want just only AD, that will be square root of 3A square. Square root of 3 remains as is. Square root of A square is A. So that is my AD value. Now that is root 3A. Now if I just consider this triangle, the triangle which we have considered now, what do I get in this? I can write ratios for 30 as well as 60 and then use the values what I have on those sides. So let's try finding the values with 30. That is for 30 degrees. sine 30. So if I'm actually going to get use sine 30 here, for that will be opposite will be this and adjacent will be this. That will be my hypotenuse. So sine 30, sine ratio is opposite by hypotenuse, which is equals to opposite is a divided by root 3 a. Sorry, that is not that. Hypotenuse is 2a, right? Sine 30 opposite by hypotenuse, a gets cancelled, that will be 1 by 2, and cos 30, which is equals to adjacent. These angles, these ratios are written based on the angles what we have considered, so that's how it changes. So cos 30 is actually going to be, that is by adjacent by hypotenuse. Adjacent in this case is root 3a divided by 2a. That is the adjacent, that's 2a, a gets cancelled, so I get root 3 by 2. So let's do the same thing, sine 60. So now if I'm actually going to consider sine 60, which is this, for that opposite will be, that will be my opposite, and this will be my adjacent. So opposite by opposite is root 3a, opposite is root 3a divided by hypotenuse is 2a, gets cancelled, root 3 by 2, and cos 60 is adjacent. In this scenario, cos 60 adjacent is a divided by hypotenuse 2a, that gets cancelled, 1 by 2. As you can see, these values actually have changed from 60 to 30, 30 to 60. Similarly, you can write tan 60 in terms of sine by cos, cot 60 as cos by sine, secant 60 is 1 by cos 60, cosecant 60 is 1 by sine 60. So we have derived 30 and 60 by using equilateral triangle, but by some construction, so that we can actually take the values of sides, and then we used those values of those sides and then the ratios to get the values. Let's try to find the value of 45. So here what we are going to do is, we'll just try to take the same right angle triangle. So let's take right angle triangle, So what happens here? I have 90 ABC. So we are actually looking at 45 degrees. So if I'm going to put 45 here, what's going to happen to the other angle? Let's see. We know that it's actually going to be 45. Angle sum property, if I'm going to use, angle A plus angle B plus angle C is equals to 180. So if I'm actually going to substitute these two values, and then I'll get angle A as 180 minus 90 minus 45, which is actually going to be equals to 45 itself. So now that by using angle sum property, we found out the angle of A. If you look at this triangle, and even if you consider AC as the base, even whether you consider or not, but if you consider as AC as base angles are equal. So that means this is supposed to be an isosceles triangle. That means AB should be equals to BC. So for that reason, we know the angles, but if you want to write trigonometric ratios, I need the lengths of sides, just because now we have shown this as an isosceles triangle with 45 degree angles. I can actually mention sides with any length, any variable. So let's find AC by using Pythagoras Theorem. So AC square equals to AB square plus BC square. So what happens? AC square is equals to A square plus a square. AC square equals to 2a square. AC is equals to root 2 a square. Root 2, I can't find anything, so I'll just keep root 2 as root 2 a square. Square root of a square is a. So that's the value of hypotenuse root 2a. So a is not under the root, it's just root 2 and a are separate. Now that we know, so automatically we should be able to write sine 45 and cos 45. Sine 45 we know opposite by hypotenuse. You can consider any of those, value is still going to be same. So I am going to consider angle C as my theta 45. Opposite is this AB and BC will be my adjacent. This will be my hypotenuse. So opposite, which is A, divided by hypotenuse is root 2a. Cos 45 is again A, adjacent, and root 2a. A gets cancelled in both cases. That will leave us with 1 by root 2, 1 by root 2. So similarly, like what we did in the previous section for deriving 30 and 60, you can actually use these two as the relationship to find tan, cot, secant and cosecant. So let's look at ratios of complementary angles. So we'll just try to get the values and try to see how we can get the values of those ratios. So for that reason we are going to consider the same right angle triangle. I'm going to consider the same thing, ABC, right angle at B, which is 90, and let's consider angle C as theta. You can consider either of A or C as theta. So I'm going to consider C as theta. So if I'm going to do that, let's try to write what we know out of this: sin theta, cos theta. So sin theta is opposite, so this is actually going to be my opposite, this is actually going to be my adjacent, and this is my hypotenuse. So sin theta is opposite AB by AC, and cos theta is adjacent, which is BC by AC. Then what happens after that? If I want to find out tan theta, which is the ratio, which is sin theta by cos theta, this by this is actually going to give me AB by BC. Cot theta will be reciprocal of tan theta, which is BC by AB, and secant theta is 1 by cos theta, reciprocal of sin theta, which is AC by AB, and cosecant theta, sorry, not that, I'll just erase that. Secant theta is reciprocal of cos theta, which is AC by BC. Cosecant theta is reciprocal of sin theta, which is AC by AB. So these are all, these ones I can write exactly based on the relationship with just sin theta and cos theta. This will be sin theta by cos theta by sin theta, 1 by cos theta, 1 by sin theta. So all you need to know is if you can write sin cos theta, you should be able to write the rest. So now angle sum property, if I take angle A plus angle B plus angle C is equals to 180. So now what's going to happen? We need to find angle A. Angle A is equals to 180, and if I transpose this, that will be minus B, which is minus 90, and if I transpose on the right hand side, C, which is minus theta. Plus becomes minus, plus becomes minus. So angle A is actually going to be 180 minus 90 is 90 minus theta. So this angle is going to be 90 minus theta. If I am going to write same ratios what we have written here, but for the angle A, which is sine 90 minus theta. So now for that reason, what is going to happen? If I am actually going to consider this, that becomes my opposite, and this is my adjacent. Hypotenuse stays the same. So keeping that in mind, sine 90 minus theta, opposite is actually going to be BC by AC, BC by AC, and for cos 90 minus theta is actually going to be adjacent. In this scenario it is AB by AC. So these ones you can continue with the same values whatever we found out. So but let's look at what is our conclusions based on whatever we have written. All we have done is we have just written the ratios, but we didn't compare anything with any of the ratios which we had written earlier. So let's look into this. What do you see? This AB by AC is equals to this, and BC by AC is equals to that. RHS, these two RHS are equals to one of those. So what can we conclude? Sine 90 degree minus theta equals to this is equals to this, but that is in turn equals to cos theta. Similarly, cos 90 minus theta is equals to sin theta. Similarly, you can write the same thing. Let's take for example cot theta. Cot theta we have written. Let's try to write cot 90 minus theta. 90 minus theta, which is cot 90 minus theta is equals to cos theta by sin theta. I'm actually going to write, once I've written this, I'm actually going to write all this in terms of only this. So which is cos theta by sin theta, which is here cos theta. I need to write here cos theta by sin theta, which is AB by AC. I need to look at these two, not the left side one. So which is actually going to be AB by BC. Now look at that. What does this look like? Cos 90 theta. This looks like AB by BC, which is equals to tan theta. So similarly, you should be able to secant, cos, cosecant, and tan. You should be able to write. So this is exactly how you need to think in terms of theta, and understand how we get 90 minus theta, and write the ratios exactly how we usually write ratios for rest of the trigonometric ratios. Let's try to prove some basic identities. So one of them is sin square theta plus cos square theta equals to 1. This is the first thing that you will encounter. So let's look into this. For all the problems, or even for deriving some formulas or identities or even ratios, we have considered right angle triangle. I'm going to do the same thing here. Right angle at 90. So that's my 90. So from the values of standard angles, we know for sine and cos the values of 0 and 90 degrees. 0 is 0, 90 is 1 for sine, and this is 1, and cos 90 is 0. So if I am actually going to take this sin square theta cos square theta, LHS, sine 0, let's take, if I take 0 angle, only I am going to consider 0 angle. Sine 0, sine square 0 plus cos square 0. What is going to happen? Sine 0 is 0, which is 0 square is 0, plus cos 0 is 1. Cos 0 is 1, so 1 square is 1, which is actually going to be 1. So that satisfies my identity. So similarly, I'm going to consider the same LHS, but in this scenario now I'm going to look for not 0 angle. I'm going to use 90. Sine, I can also write this as sine 90 whole square, which equals to sine square 90 plus cos 90 whole square. Here in this scenario, 90 sine 90 is 1, 1 square is 1. cos 90 is 0, 0 square is 0, so which is actually going to give me 0. So in both cases actually I was able to prove that sine square plus cos square theta, theta here was 0 and theta here is 90. So let's call this as case 1 and this is my case 2. Now let's look into case 3. We knew the values here, we were able to substitute and we were able to find out or prove that particular identity. If theta is an acute angle, here we had taken only 0 and 90 straight away, so let's take C as 90. I'm going to consider angle C as 90. So if I'm actually going to use that, I need to write the names of the sides. Opposite to that, this is going to be opposite, this is going to be adjacent, and that is my hypotenuse. So let's go back again. We'll use the same LHS, sine square theta. So let's try here. Sine theta will be equals to opposite by hypotenuse. In this scenario it is AB by AC, and cos theta is actually going to be BC by AC. Let's just substitute those values in sine theta and cos theta. Sine square theta, which is AB by AC whole square, plus BC by AC whole square. This is my sine square theta and cos square theta ratios based on the sides of that triangle, and this is my LHS. So this will be AB square divided by AC square plus BC square. I am squaring both numerator and denominator, AC square. So if I take LCM, AC square is common for both of them, so the top numerator will be left with AB square plus BC square. So what do we have from AB square for BC square? If I'm actually going back to if I'm going to go back to my diagram, and if I use Pythagoras theorem, AC square is equals to hypotenuse square is equals to sum of the squares of the other two sides, which is AB square plus AC square. This is the numerator here. Sorry, here this is not AC square, AB square plus BC square, right? BC square, sorry. So that's a numerator which is equals to AC square. So that means I can substitute that as AC square divided by this AC square. AC square, they get cancelled, I get 1. So which is equals to RHS. So we have proven there are 3 cases that we have taken, one with 0, another one with 90, another theta is acute angle. And here we wrote the ratios based on sides, and then we have proved that sine square theta plus cos square theta is equals to 1. And now let's try to prove these two identities, simple identities, but just let's just have a look how we can get these two proved. So for this I'm actually going to go with again same triangle, some initial things that I'm going to write which will be easier for me to write other ratios here. So ABC, right angle at B, and here as you can see that theta is mentioned, so I'm going to take C as theta, even you can go for A as theta angle, C as theta, and then I'm going to write, just as you know already, I'm actually going to base rest of the ratios just with sine and cos, so I'll write the ratios in terms of sides. That will be my opposite, that is my adjacent, and that's my hypotenuse. So opposite by hypotenuse, which is actually going to be AB by AC, and this is going to be BC by AC. These two are based on angle theta, where C angle theta is, that's what we have considered. So based on this, if you want to derive these two, so we will be able to use this sin theta and cos theta. Here all I can see is there is tan theta and secant theta, both are acute angles, so 1 plus tan theta. So how do I do this? So what we can do is secant theta From Pythagoras theorem, what can we write? We can write that AC square equals to AB square plus BC square, right? AC square equals to AB square plus BC square. So now let's see if I am actually going to write ratio for secant. Secant theta is equals to 1 by cos theta, which is equals to reciprocal of this, which is going to be AC by BC. Here we have secant square theta, so that means I should be able to get AC square by BC square. So AC square is there, I don't have BC square. So let's divide the whole equation by BC square. The reason why I am dividing by BC square, because on the right hand side here I can see that secant theta is there. Secant theta ratio, if you look at from the diagram, is reciprocal of cos theta, which is equals to AC by BC, which is that. And if I am going to come back to my Pythagoras equation, what I have written, AC square is there, but I need AC square divided by BC square to get secant square theta. For that reason I am going to divide the entire equation by BC square. So that will be BC square and that will also be BC square. Let's separate the RHS terms. AC square BC square, AC square by BC square, which is equals to AB square by BC square plus BC square by BC square. They both get cancelled, so I'll be left with 1. AB by BC. What is AB by BC? These can be written as, remember that these can be written as AB by AC by BC whole square and AB by BC whole square plus 1. So let's say if I am going to write tan theta. Tan theta is sin theta by cos theta, which is actually going to be this by this, AB by BC. So here AB by BC is tan, AC by BC is secant. So automatically I'll be able to replace them with secant square theta equals to tan square theta plus 1. That's what we have proved. So similarly we can do the same thing for this as well. Cot theta is actually going to be reciprocal of this tan theta, which is BC by AB. So let's take same Pythagoras. AC square equals to AB square plus BC square, right? So now what do I need? I need, on one side I need cosecant square. Cosecant can be written as cosecant theta is reciprocal of sin theta, which is in this scenario AC by AB. That is that one. AC by AB, just reciprocal of sin theta. So now looking at this cosecant square theta, that means this has to be AC square by AB square, but here I have AC square, so that means I need to divide the whole equation by AB square. So that way that will turn into AC square by AB square equals to AB square plus BC square whole divided by AB square. Again we'll separate the terms in the numerator, AB square divided by AB square, and the denominator plus BC square divided by AB square. These two get cancelled, so I'll get 1 there. What is BC by AB? Let's look at BC by AB here. BC by AB is cot theta, that is cot square theta here. AC by that is AC by AB. AC by AB is cosecant, that will be cosecant square theta. That's what we proved. So in this scenario all you need to do is start with Pythagoras theorem, look at what is given and then decide what to divide with so that you can get that, and then separate the numerator terms with the denominator and then cancel each other, and then you will arrive at those identities.